Welcome to the 20th lecture, and today we are going to talk about the non-Abelian gauge interactions. So we have talked about the last thing we mentioned in the previous lecture when we are talking about the non-Abelian gauge symmetry is that most general Lagrangian involving with a minimal number of fermions and minimal number of scalars can be written like this. So this is Fa mu nu. Fa mu nu is just the pure gauge part, which I am writing as Lg over here. And this is the part where the fermions are. So this is the n component, some number of components in the fermion field. Okay, and this is the Lf, and here is the phi field. Okay, so this is the minimum thing you should write when you write a fermion or the scalar along with. So if the Lg plus Lf is the interaction Hamilton Lagrangian for the gauge boson plus the scalar plus the fermion, sorry, and all one has to do is to have this covariant derivative over here that takes care of all the interaction between the fermion and the gauge boson. Okay, and here similarly we do it for the scalars, and here also the covariant derivative takes care of the fact that the scalar is going to interact with the gauge boson. So today, in today's lecture, we will discuss how exactly that happens and a couple of things that we'll mention over here. So psi of x transforms using u psi of x. I want to put the label psi on u just to say that psi transforms like this and the phi transforms like u phi of x. And when you write u psi, an expression for u psi is exactly as it was. So it is exponential of I theta of x a t a, but then I'm putting the label psi over here. Reason is that fermion belongs to a certain representation of the gauge group, which is in the case of u1 we had a similar thing over here. There was a q operator was sitting over there, you can just say, or the number, the charge exactly. Okay, so this ta basically takes care of ta psi, takes care of the fact that the psi transforms under certain representation of the symmetry group. Okay, and phi could be from the different symmetry group, and I can just elaborate that with certain examples. But first, for completeness, just say that psi transforms in this way using this u psi matrix, and phi transforms using u phi matrix. Both of these unitary matrices can be labeled by same theta x a, but the corresponding ta matrices, the generators, are different because they belong to different representation. Okay, so these are the particle representation matrices. On the other hand, A, the gauge field, only transforms as a function of theta. It doesn't much care about the representation, that because A mu A belongs to a given representation, which is called the adjoint representation. And here the TA satisfies TA TV equal to I times FABC TC. Pardon me, I forgot to write TC. Okay, and they are normalized to trace of TATB is equal to delta AB half. Okay, so we did this, and here when I say TATB equal to I times FABC TC, this is valid for both TA phi and TA psi, because TA phi, TA psi are the specific representation of this abstract matrices in general. So this will define this particular commutator will define the Lie algebra per se. Okay, so let's make a note of a couple of things. So FABC, basically this thing appearing here, or basically the guy that appears on the right hand side of the commutator. This commutator FABC, values of FABC defines what algebra we are looking at. Okay, and of course the range of these variables ABC, how many of these things I have. So basically FABC defines the symmetry algebra, and hence LG, because LG doesn't depend upon anything else. F mu nu is a function of A mu, which transforms as such. Okay, now psi A and psi x and phi x, and hence the corresponding matrices, belong to different representation of the symmetry algebra, which I just said. Okay, and the example would be that if the symmetry algebra is SU2, here I want to elaborate with an example. The algebra would be this FABC is nothing but epsilon ABC. So this is a fully symmetric fully antisymmetric tensor, the Levi-Civita symbol. And here A, B, and C ranges from 1, 2, and 3. Okay, so for the case of SU2, we know this angular momentum algebra. And one example would be that the psi belongs to j equal to half or two-dimensional representation. Okay, and then TAs would be nothing but polymatrices by 2. And assume that phi belongs to j equal to 2 representation here, and j equal to 2 representation is a 5-dimensional. In that case, the TA matrices will be 5 cross 5 matrices that can be obtained using the angular momentum algebra. Okay, and angular momentum algebra you already know, the matrix elements and all these things you already know. So in principle, I can have two particles. They don't have to be Fermion and Scalar. Basically, let's just forget about which spin they belong to, but just two particles that can transform differently under the same group. Okay, because they belong to a different representation. An example here is psi belongs to spin half representation, phi belongs to spin 2 representation, and that's very much possible, the choice. And so most generally one can write things for this particular combinations, such combinations. So today basically what we want to discuss is how we visualize this Lagrangian that is written over here, and how many terms this compact Lagrangian has. So it looks pretty compact over here, and a lot of things are kind of understood, but let me just write them explicitly. So let's start with this LF being written. So LF is I times d mu psi, d mu gamma mu psi minus m times psi bar psi. Then I can just expand it, is I times psi bar del mu minus ig a mu. A mu is a blackboard font, so it means it has already the TA matrices. The gamma mu times psi minus m psi bar psi. And so here I just separated this piece, and this is the piece that we got where the A mu A is coupled to something, and that something happened to be the forecurrent. Okay, so because the psi bar TA gamma mu psi, so just assuming psi bar gamma mu psi would be a kind of vector current. TA just says that which component of psi mixes with which component of psi. And to make it further elaborate, we'll just say let psi be an n component representation of the algebra. Okay, so what it has, psi 1, psi 2 all the way till psi n as a column vector. Okay, now each of these psi 1 and psi 2 are actually 4 component Dirac spinor. So that is important thing to note, that if I have in this particular example, when I say psi is j equal to half SU2, it means I have psi 1 and psi 2, but psi 1 is a 4 component Dirac spinor. Okay, and just a moment. And all the components are the basically 4 component Dirac spinor of this guy. Psi is without any index, is n component object. So psi bar would be psi 1 bar, psi 2 bar, and so on in a row form. So clearly from here, psi bar psi is nothing but psi bar I psi I, where sum over I is assumed using Einstein notation. But here both the i's are appearing on the lower. They don't have to appear one up, one down, because there is the metric over on this space is just 1 because it's sum over this thing. Now if I write psi bar gamma mu psi, okay, so that is just nothing but psi bar I gamma mu psi. So this is again sum over I is assumed. Psi bar gamma mu del mu psi is will be psi bar I gamma mu del mu psi I, here in terms of the components of this field. Okay, one can write it like this, where a certain assumption is made that repeated indices are summed. Now let's look at psi bar TA psi. Okay, so what happens is psi bar I psi j TA ij, and this is just a complex number, so I can write it anywhere. Okay, that's why I wrote it separately. Here I could not have done this because both the psi i's are different Dirac with this 4 component objects, so gamma mu has to sit in between them to make sure all the unwritten indices are contracted properly. Okay, now if I have object like psi bar TA gamma mu psi, basically what I'm saying is psi bar I gamma mu psi j, and what is multiplying it is TA ij. Again, TA ij is a complex number, so I can write it anywhere, but gamma mu must sit between two sides because those 4 component indices defining the 4 component I'm not writing explicitly, these are written implicitly. So the order has to be maintained in which so that we know what is contracting with what. So basically, using these relations, I can write LF is I times psi I gamma mu del mu psi I. So that is using this particular relation over here. Okay, and this is G times psi I bar gamma mu psi j ta I j a mu a. Here I am using this particular relation. Okay, and this is the element of ta psi ij. Okay, and this particular thing from here to here, including the ta, is the 4 current, exactly like here, because it's just I'm writing this in a component form. Okay, and of course m times psi bar I psi, which is just using this relation. So here I want to just emphasize that certain notation that we are going to use. When I say I, j and k, they will be called the matter index or the representation index, which is the index with which the components of the fermion or the scalar will be labeled. Okay, so here we have fermion. So psi I means component I or j is a component of this multiplet. Okay, and since this multiplet is a representation of algebra, it is also called representation index. And usually in this representation we put the matter field in while doing the model building, so we also call it the matter index. So that will be denoted by I, j, k, l and those variables. Using A, B and C, we use the gauge indices like the TA or A mu A. They also call the algebra index, or you can call it the adjoint representation index, because we'll just describe what adjoint representation is, and the mu, nu, rho, sigma will be the Lagrangian indices. So since these objects have a lot of indices, and yet I have not written one index explicitly, they are still implicit, which is that psi 1, psi 2 are 4-component Dirac spinors. So there is no index I am introducing to access different components of the Dirac spinor, because I'm going to use that implicitly. Okay, I'm not going to write those indices explicitly. This is the reason why I'm writing the psi bar gamma mu psi, all these things in the correct order, to say that the spinor indices are matching. Okay, now before we move ahead, let's just iron out a couple of things about our language, which is that, let's say A is a symmetry algebra, usually the Lie algebra. Then what happens that A is also a vector space, because every algebra is a vector space. This we have discussed in mathematical physics course some 3-4 semesters ago. And for any algebra we can find a representation, and for case of SU2 we also did that. And SU2 representation, you know it from quantum mechanics courses as well. So a representation basically is a map from A to a set of operators acting on a vector space. So we choose a vector space, and this vector psi belongs to that vector space, and this TAs will be the matrices acting on this vector space. So that is, the TAs are element of the algebra. And so what I do by representation, I choose a vector space, and the operators acting on this vector space satisfying the same algebra as the original algebra will be considered as a representation of that algebra. So that's how the representation theory works. Now what is special about adjoint algebra, adjoint representation, that it is a map from A to A. Here the algebra, which is a vector space, so I choose this particular vector space. So operators of A acts on the vector space A itself. Okay, so that's adjoint representation. So that is fixing a representation. Reason why I didn't need anything in the transformation of gauge guy other than FABC. Okay, so that's the only information it has about, it requires for the transformation property, while any matter, any other representation actually require the transformation, sorry, the representation of this generators. Okay, and for adjoint it is kind of defined. Okay, so let's move on to the scalar case. So d mu phi dagger d mu phi minus m square times phi dagger phi. This is my Lagrangian, scalar Lagrangian, and phi is just n component object, so phi dagger is just n component row. Phi dagger phi will be written as phi I dagger phi I, sum over I is understood. Okay, so d mu phi I can write is, so del mu times identity, this is a n cross n identity matrix, plus ig a mu a times phi. Understandably from here I can write d mu dagger as such, where the derivative is acting to the left here. That's why this arrow on the top indicates, because it's just a dagger of this particular expression. And since a mu dagger is a mu, that is because TA dagger is TA, So it's a Hermitian matrix. So I can write this guy with only changes, plus minus I becomes plus I over here. Okay, so now if I take ith component of this guy, then d mu phi ith component is nothing but d mu phi del mu delta ij minus I times g a mu a t a I j phi j. And of course when you multiply this delta ij, make it del mu phi I minus ig a mu a t a I j phi j. And here also we can just take the conjugate of this particular guy and write it over here. Okay, so there's just there's no special thing, it's just that I going to minus I and all the indices are taken care properly. Okay, so now let me just say that I'm going to multiply d mu phi I. So here the summed over index is j, and here d mu phi I dagger, here summed over indices is k. I chose the dummy indices differently in these two terms so that I can put them here. So d mu phi dagger d mu phi will be this expression in matrix notation. Okay, well, phi dagger del mu a times identity matrix and all that, this is just a del mu phi dagger, and this is just a del mu phi. Okay, just copy it from above, and when you write in terms of the components, then you basically copy you copy this guy onto the left and this guy over here onto the right. So this is the copy paste, so I'm not reading it again. Now this is a 4 terms. So first term with the first term just gives you the standard n component scalar kinetic piece, which is del mu I phi dagger del mu phi I. Okay, then let me do the second term with the second term. That gives me g square phi dagger tb. So this is, I say, phi dagger tb a mu b. A mu b is written over here, and ta phi ij phi aj. Okay, so here I is summed over, here tb ki is there, and here tij is there. Okay, so this are the matrix multiplication in a way because I is summed over, and this is a row vector and this is a column vector, and here b mu and a mu are sitting here. So this indices are contracting with each other. So this is the 4-point interaction involving 2 scalars and 2 gauge bosons that you get. And then comes the cross terms, where del mu phi dagger with this coupling and tij phi j is sitting over here coming from the second piece, and a mu a is sitting over here. Okay, and here the first piece will be phi dagger taab mu, and del mu phi I from here is multiplying. Now this thing marked in blue I'm going to rewrite over here by renaming the variables. For example, all the phi daggers will have the index k and phi will have index j. Okay, so here I just j is there, so I just remove this, rename phi I dagger to phi k. So this is just the renaming part which goes over here from here. Okay, so that's only one renaming is done. And second thing, all the Lagrangian index on the a goes upper, so I just brought this del mu down. Here del mu was up, here del mu became down. Okay, so that's the only change from here to here. The contracted Lagrangian indices are changing places, and the contracted one of the matter index is changing its name. And similarly I do for the second piece. Here mu was already up, and here I rename the second variable as a j. Okay, then while doing this, after doing this, what happens is that the ta, okay, and here also it was b was the index, so it renamed as a over here. So what happens that here it was what was coming tbki, and here taij was there, but what if you do the appropriate renaming of the dummy indices, both of this becomes takj. Okay, here and here, so I can take that common, and a mu a was also there, so I can take that common. It's just a simple repositioning of the summed index and renaming them. Then what I get is over here is I times g phi dagger del mu phi j, phi dagger k del mu phi j minus del mu phi k dagger phi j. Whole thing is contracted with ta kj, and that is contracted with a mu a mu. Okay, so these things in the square bracket marked in pink over here is a fork current. Okay, so here of course k and j are indices, but then they are contracted with ta kj, and A is the index, but then it's also contracted both over here. But one has to be careful. For each value of A, I have a separate gauge boson. So for each gauge boson, I need a separate current, and which it provides for a given A. You sum over all gauges to get me this number. Okay, so this is basically my current, and if I write this current in the vector notation, it will be phi dagger TA del mu phi minus del mu phi dagger TA phi, and whole thing is contracted with A mu A. Okay, so you see this humble looking term over here actually is sum of 4 terms with all these structures in it. Okay, now and similar, like a lot of structure, but there was not manual structure for the fermion, but here we see a lot of TAs hanging around, currents and all these things. Now next thing to go do this thing, the writing is the F mu nu. Okay, so this is a gauge Lagrangian, which is minus F mu nu A, and here I'm just writing F mu nu upper and lower separately with a different dummy indices. Okay, so let me just go for that and discuss some properties over. So F A mu nu is del mu A del nu A, del nu A mu A and del nu A mu A times G F A B C A mu B A mu C. So this is defined over here. So here the B and C are the dummy indices that is summed over, and A and nu are the free indices. Here A mu nu are the free indices again, and here dummy indices, instead of writing them B and C which were written over here, I'm calling it D and E, because these two have to be multiplied in the same expression. I don't want to have more than one pair of the contracted index. So for each contracted index I'm using a different name. Okay, now before I jump on to finding the expression, let's look at what happens when I exchange mu and nu. So obviously this first part we knew from the U1 gauge bosons or electromagnetism also. If we extend mu and nu, it is antisymmetric for each value of A. Perfect. Now I can do the same exchange over here, but it looks like if I exchange mu and nu, nothing much changes. But then I have to be careful. Wherever mu appears on the second term, it appears with B. So mu and B is a kind of a doublet, and nu and C are kind of doublet. So when I'm extending mu to nu and vice versa, I also have to exchange B to C, right? Because mu B will go to nu C and vice versa. But under that transformation, this is purely symmetric. Right? It goes to itself, and A commutes with this. These fields commute with each other. Pardon me, they commute with each other. So I don't have to worry about in which order I write them. Okay, but when I rename B and C, then FABC will become FACB, and when I bring it back to original form, it will pick up a minus sign. So basically what happens that both the first term and the second term is actually antisymmetric under such transformation. This can be seen not just for the lower index mu nu, but also for the upper index mu nu. So now what I do, I put this expression over here in the expression for the Lagrangian, and there are 4 terms here, because each one I can consider this, the bracketed part is one term. Okay, and not expand them separately. So I have one term which is the first contracted with the first one. This is sitting in the first line. Then I take something with the second contracted with the second one, which is sitting on the second line over here. Okay, since each of these terms coming from the expression of F mu nu is antisymmetric, the combination will become symmetric. Okay, so first term times first term over here is all we already have. This kind of term we already have studied for the case of U1 electromagnetism. There are 3 more kind of terms over here, actually 2 more kinds. So here is the 4 of the mu's. A mu's are put together, which is combination of second terms with the second term. When I take the first of here and second here and the vice versa, then I get term over here. So here is the second term of the upper index, so it is F DE AD mu AE mu times this guy, and likewise here. No need for me to read it. Now this I'm marking, last 2 terms I'm marking in yellow, because I can I have to rewrite them in a way. So first of all, let me look at this particular term. Okay, And okay, so I did not use this thing very carefully, I believe. So let me just take any one of this term. Okay, so the two terms are already there, and up to relabeling of indices upper and lower, they are one and the same. Okay, so here if I just call it A, B, C and lower the indices of mu and nu, you will see that this term is exactly same as this term, so it's basically g by 2. Yeah, so combine these two things, what you get is minus g by 2 FABC, and this particular term, instead of writing as it is, I'm making sure that the derivative is acting on a row. Okay, but I know that here the derivative is acting, let's say here derivative is acting on a nu a. So a is as it is, upper the gauge index, just I have to convert nu into a row, so that's g nu row is doing that task. So I'm just deliberately putting this, and likewise here. Okay, second term, the derivative with regard to nu was there, sorry, the derivative of a mu a is there, and so here mu rho is will come. Okay, now it is as if this particular operator over here, which is g nu rho del mu minus g mu rho del nu, is acting on a mu rho. Okay, that's what will give me this piece, times ab mu ac nu, which is here, just keep it above. Okay, and mu nu is lower here and mu nu above here. So this particular thing, if you look for, okay, just this piece, okay, this is again completely symmetric, the way, because it's a cross term between an anti-symmetric piece with an anti-symmetric piece. Okay, that has to be symmetric. But if you look carefully what it is, so if you just look this part, and let's just say you swap b mu with c nu. So if you swap b mu with c nu, this goes to this, no change. Okay, but what happens inside when nu and mu are exchanged, then this particular term becomes negative over itself, which is the original property of this guy. Okay, it's just written differently, or written differently over here. So actually this piece overall is totally antisymmetric, is antisymmetric under this transformation. Okay, but then FABC is also antisymmetric under transformation of B, exchange of B and C. So overall we are the same. Okay, so this is basically symmetric under exchange of these two guys, and that makes sense, because if you exchange two bosons, because this is supposed to represent bosons, then you should not get an additional sign. Perfect, amazing. So what is happening over here, that I can exchange these two guys, but what about exchanging a mu, a row with a b mu? Okay, why these two guys, or why not this and this? And that because the way Lagrangian is written. But since it is symmetric under these two, okay, and FABC is totally antisymmetric, it means this particular part I can write in a form which is totally symmetric. Okay, so here you see the term is minus g by 2. What I do a permutation of this kind. So a rho b mu c mu, I take this, and let's say first term represents this particular orientation. Okay, then what you do, you wherever you see a rho, you replace it by b mu, wherever you see b mu, you replace it by b mu, and wherever you see b mu, you replace by c nu, and wherever you see c nu, you replace by a rho. Okay, then what you'll get from the first term is a second piece, where nu is replaced by rho, rho is replaced by mu, and mu is replaced by nu. Okay, same thing over here and same thing everywhere. And then you again act on this term, the same permutation, to get this guy. Now if you ask what happens under b mu and c nu exchange, then we already confirmed that this part is negative over itself, and then b and c from outside will also be antisymmetric. So overall it is symmetric. Now what happens here? So if I exchange b mu with c nu, what happens? This b mu and c nu, this goes into this and this remains as it is. So this piece will go into that piece. That's perfect. But what happens that if you look at this guy, okay, so mu and nu exchanged, so derivative with regard to mu and g rho nu should come. So this guy goes to this guy. Okay, and then what you notice over here, and b mu goes to c nu. Okay, that's also perfectly fine. So this term goes to this term with opposite sign. So actually, under this transformation that is written over here, this term goes to minus of this term and vice versa. So overall, everything under this curly bracket changes sign. So this goes to minus of itself, this goes to minus of this, and this goes to minus of that. So what's important, that everything under curly bracket changes sign, and so does FABC, because B and C are exchanged. Now, having written in such a nice symmetric manner, I can take any pair from this set of three indices and exchange them, and what we will see, that they are exactly the whole term is exactly symmetric. And this is very important, because we want this exchanges to be done while drawing the Feynman diagram. So I want to write my Lagrangian in a way that these terms are totally symmetric. And similarly, like this is what we did for this yellow mark term in the Lagrangian over here. Okay, but I have this four guys term, four gauge boson interacting over here, and I want this term to be symmetric under any pair of gauge boson exchange, and that can be again constructed in a similar manner. Okay, there are no derivatives here, so this will be slightly simpler. Okay, so for the 4-point interaction also one can symmetrize it, which I have not written. And as far as the quantization of this fields are concerned, for quantization I only need to care for the part which is quadratic in and that part is just so many copies of the u1. So whatever I did for u1 simply goes forward over here. I have no change. And just to make sure that pi 0 a, that the field momentum corresponding to a0 for each value of a is 0, you can just check, because this is anti-symmetric. So you will never find time derivative of a0 appearing in the expression of the f mu a itself. Here a's appear without the derivatives, and when the derivative appear, mu and nu can never be same. So I cannot have the time derivative of a0 appearing in f mu nu. So corresponding momenta is 0. All the gauge issues that we had in u1 case are here, no change. And so the solutions are exactly the same. The Gupta-Bleuler condition we have to apply. We have to fix the gauge condition and apply that Gupta-Bleuler condition to get to a situation where we can do a quantization of this theory. Okay, so with this I would say a major part of the gauge interactions are done. I have to explicitly remind you that when I write a Lagrangian like this, although I'm writing the d here and the d here same, the meaning of d depends upon what it acts on. This is what I also explained for the case of the u1 gauge boson. Here it is true for the non-Abelian also, and one has to make sure that we are using the right representation matrix, which is the u1 case. It meant that you are using the correct charges while writing the expressions. Okay, so with this I will say that this particular innocent looking gauge non-Abelian Lagrangian is actually sum of many terms with all the gauge invariants, and what it doesn't have is a gauge fixing term. And I don't want to do gauge the quantization of this guy, non-Abelian guy, in Gupta-Bleuler method. It is not very difficult. It's just that I will do it in the path integral formalism. It's just the n copies of the same stuff, and one has to, the bookkeeping increases because there are more indices to take care of. There's nothing more than that actually worries. So but the non-Abelian thing will look more attractive if I do it in the path integral formalism. So from there will be one homework that I will give you, and afterwards I will move on to the path integral formalism of quantum mechanics, which I'll convert into the field theory, and then we'll do the path integral quantization of fermions and the gauge bosons. Okay, and then we'll move on to renormalization and all these things. So as far as this lecture 20 is concerned, we are done. We have seen in detail how to write various kind of indices when we write an innocent looking Lagrangian like this. So hopefully you appreciate the gravity of the situation.